The third lecture on Fortran programming. In the earlier two lectures we have learned basics about Fortran programming, that is how to name a variable, and we found that the variable names should start with an alphabet and it should not involve any symbol used to represent mathematical operations, and if the variable name starts with an alphabet within the range A to H, it is real, and so is in the range O to Z, and the variable name starting with I, J, K, L, M, N within this is integer. It is the default setting of Fortran language. And then we have say the Canto statements, the two types of Canto statements. One is the if statement. If statement is if some question is asked, then in this part when the condition is satisfied, these parts are executed, and then the alternative is through else. And when the condition is not satisfied, the lines between else and end if these are executed when condition is not satisfied, and these steps are executed when condition is satisfied, and after this it comes over here. And alternatively, when the condition is not satisfied, right from there the program comes to there. So it controls the logical flow. In natural way, the program proceeds from one line to the next and then next. Here the controlling is done. Another type of controlling we have introduced through the go-to statements. We can anywhere as we desire or as is required, we may say go to statement number, and it will find this statement number between the column 2 to 5. The restriction is that the statement number between this and this is must be a non-negative positive integer in the range 1 to 999, and within a program there should not have two lines having the same statement number, because it will create an ambiguity. With this I come to the Fortran library function. In many cases we found that we need to calculate square root of some quantity, say some quantity x, and we need to calculate square root of x. The evaluation of square root is not an easy process. If we have to write the program by ourselves to calculate the square root, it will be the program will be lengthy. On the other hand, these such calculations occur very frequently in numerical calculations. So there are provision within the Fortran for the calculation of these things. You need to know what is the exact grammar used for calculating this. As for example, in Fortran we write it sqrt within bracket x. It is the argument, then it is equivalent to Fortran mathematical symbol of square root x. But before using this, I want to point out few precautions. Say we need to calculate b is equal to square root of a, and with a is equal to say 3. Then we may do one thing. We may call a is equal to 3 and then b is equal to square root of a. Then what happens that since this is a real variable, even if we supply 3 from output from keyboard for the value of a, it immediately goes to 3 points because it is a real variable. Then here it comes the square root of 3, that is 1.73. So the value of v that is assigned is 1.73, etc. This is one way of doing this. If we do it in this way, b is equal to square root of 3. If we use the argument as Fortran constant, here the argument is a Fortran variable and the value of the variable will be assigned by its nature. A is real, so it has been taken as real. Here we have used a Fortran integer, Fortran constant, which is 3 in integer mode. So it assumes that you want the result in integer mode. So initially it calculates 1.73 and strikes off all the things to the right of the decimal number. So it is 1. So 1 is assigned to B. So 1 is assigned to B, and since B is real, the result is 1.0, which is not 1.73. This is a point of precaution. You must be careful whenever you use Fortran constants directly as the argument of any function. Third way of doing it is B is equal to square root of 3 point. It gives you the correct result because it is in the real mode. With this, I am going to list few functions here and the precaution will be stated. And another thing is that A must be greater than equal to this. The constant A, that is the argument, should be a real argument, non-negative real argument. So to say first one is mathematical statement and then Fortran statement. Square root of x is sqrt of x. Restriction x is real and greater than equal to 0 point. Second, sine. If you want to calculate sine of x, then it is sine of x. We write it sin. They are case insensitive and the value is x in radian. That is to say, if you want to calculate sine of 90 degree, then writing of sine 90.0 does not give you 1 because it is not in radian. So first thing that we have to do, we have to convert the value in degree into radian. That is x in degree to x in radian. That conversion is needed. This conversion is needed. When we put the input in this form with xd is equal to 90, you get the correct value. Similarly, there are compilers which also takes this function, but this function is in general not available in free softwares of Fortran. This sine in degree. So if we write sine d 90.0, this is indeed equal to 1.0, but sine 90 is not this. Similar thing is cos. For cos it is cos, for tan it is tan. So there are other functions of this category, cos function and tan function. Sometimes we need to calculate pi. And how do we calculate value of pi? If we the problem is that given the radius of a circle and you need to calculate perimeter is equal to 2 pi r and area is equal to pi r square. So what should be the value of pi? We can use pi is equal to 3.1415 etc. But it is an approximate one. There are better way of calculating pi. I am going to this. Sine inverse x. Sine inverse x is written as A sine of x. A for arc sine. Arc sine, actually the sine inverse is the arc function. Originally they were named as arc function, so this A is from arc, and it gives you the value of the value, and this must be always in radian. So if we write tan 45 degree is equal to 1, or in radian tan pi by 4 is equal to 1. So if we write tan inverse 1 point, the result is pi by 4. So if we multiply it by pi, or one way of this getting this value of pi, cos inverse minus 1 point. Do not forget to put this decimal point. This is the value of pi. So these are the utility of the inverse trigonometric function. They are again a cos, a tan, etc. This is a very important way of calculating pi. You need not to give the approximate value of pi. It will be calculated within the program. The sine hyperbolic function, sine hyperbolic x. This is SINH of x, sine hyperbolic of x, e to the power x. This is EXP of x. There all the arguments are real and related to radian, and the input output is IO is in radian. Then comes to log function. There are two types of log: natural log, LOGX. This is log base E, and Napoleon log, log base 10. It is LOG10X. This is 10, 1010. Then sometimes it is required to convert an integer number into the corresponding real number. As for example, when we want to calculate the average, then this is the average over xi divided by number of observation. Then to avoid mixed mode operation, one need to convert it into the corresponding real number. Say n is equal to 10, then we need to convert 10 to 10.0. How to do this? There is a function float. Float n gives you the corresponding real number. Here the integer is the argument is an integer argument. Sometimes one need to get the reverse way. So we have a real number, from it we want to get its integer part only. Say for example, we have 2.973 and one is interested about its integer part, which is 2. So this is done by integer fix command. I fix 2.973 is 2. So I fix is integer part. Not remember that this is not the nearest integer part. It is the integer part. Even if it is 2.9999, even if it will give you 2. If one sometimes we need the nearest integer, that is the integer which is nearest to the real number, then it is NINT, nearest integer. The nearest integer of 2.97 would be 3, and it will obey the statistical law of statistics, that is if you write NINT of 2.5, it will give you 2, but if you write it 3.5, it will give you 4. So the law of statistics is that if you approximate anything which is less than 5, then the preceding character remains, the preceding numerics remains the same. If it is greater than 5, then this is increased by 1, which is done here. And what happens when the neglected digit is exactly 5? Then the preceding digit remains the unaltered if it is be even, so this, and it is increased by 1 if it is be an odd. So it NINT will also follow this rule. This much with the another thing is very important is absolute value of x. And absolute value of x, in the earlier class we have learned how to calculate, how to make a program for absolute value. It is simply ABS of x. It will give you the value of absolute value. So with this much of Fortran library function, we proceed to the example that I have promised, that the solution of a quadratic equation. For other library function, you may consult the table provided at the end of any Fortran book. Now the problem is that to find out the roots, to find the roots of a quadratic equation. Now we know that a quadratic equation is this: ax square plus bx plus c is equal to 0. When we say the equation is quadratic, we have in mind that a is not equal to 0, otherwise the equation would be a linear. And the roots is that x is equal to minus b plus minus b square minus 4ac upon 2a. You know that if a happens to be 0, then this expression will be undefined. So we must be taken care of the fact that a is not equal to 0. And the roots are real. If b square minus 4ac is equal to 0, we have repeated roots. If this is be greater than 0, real unequal roots. And if it is be less than 0, complex conjugate roots. This is the theory behind this. So we start writing the program. This is 1, 2 to 5, 6, 7. I hope everything is noticeable. Yes. Now, first thing, read a comma b comma c. First we check for that a is, if a is equal to 0, this is a wrong statement, because by a we mean a real variable, and we cannot compare a real variable with an integer constant. So actually we must write 0 or at least 0 point. If a is equal to 0, I want to stop the program, so I write stop. Or you may say, or you may write then not a equation. Then I write stop. And in this case, what I have done, if a happens to be 0, if someone provides the value of a to be 0 by mistake, the program will give you a warning that this is not a quadratic equation as a is 0, and the program stops. And we must write else and end if. Instead of writing these two lines, we may not write this else and write else if. When the program finds that there is no else part, that it means that if calculation ends over here. So whenever a is equal to 0, it writes this one and program stops here. If a is not equal to 0, the program comes right there. You see, whatever the roots, this quantity comes in the denominator always. So we define denominator first. Den. Denominator, we write, by den we write 1 upon 2a. So we write it 0.5 times 0.5 by a. So you must multiply by den, not divide by den. Then we come to the calculation of the discriminant. So discriminant is b square minus 4.0a star c. Here sometimes one writes it as 4, which is not correct one. You must write 4 point because the entire calculation has been done in real mode. Then we need to ask the question whether d is greater than 0 or less than 0, etc. So I keep a line of blank here and then ask the question, if d happens to be greater than 0, then the roots are real roots then. First root x1 is equal to minus b times square root of this thing. We calculate it as ds here, but d may be positive and negative as well. So we write square root of so what we do, d, square root of d. So what we are doing? We are using function within function. So first what is it does, say d is equal to minus 5, d is equal to minus 5, then absolute value of d converts it into plus 5, and then it calculates the square root of mod 5. So we write it as minus b plus ds into den. You see the den is 1 upon 2 pi, so we need not to divide it by, and then x2 the second root is minus b minus ds times 10, and we write here the real roots. Colon, you should not put comma. x1 is equal to blank value of x1, comma, a blank, x2 is equal to blank, comma, x2. So it writes first x1, first writes real roots, colon x1 the value of x1, and then x2 and value of x2. Else if d, so this, if d happens to be negative, then the program from here directly jumps over here, and the roots are complex conjugate roots, so we need to write xr, the real part of it. Oh, let me come to this side. After else we write xr is equal to minus b star 10 and xi is equal to ds star 10, and write CC roots, complex conjugate roots are XR is equal to blank real part, XI is equal to blank XI. Then end if, stop end. One deficiency of this program, that is, this program has never written the input supply, so it would be better to write A, B, C just after this one. We could do the program by same program using the go to statement. For doing this, this part will, up to this part will be the same, and then I change the rest of the part to redo the program using go to statement. Before going to this, I want to say some simplification of if statements. In general, the if statement is this: if question, then else, and if. Earlier I have stated that whenever this alternative part is not there, you may omit this. There are certain occasion arises when we need to do something, a single executive statement, only when the condition asked is satisfied. That is, if we write if some condition and then an executable statement, then what the program does is that whenever this condition is satisfied, it calculates this one. When the condition is not satisfied, it doesn't execute it, and the conditional calculation remains confined only this particular line. So with this knowledge, I am going to rewrite this program using go to statement. If t is equal to 0.0, go to say 1. If b is greater than 0, go to 2. So then we write and write CC roots exactly. So okay, after that the program goes there and it writes this one, calculates XR, XI and write. Then within 2 to 5 column, I write say 2 first. Then this is the case when we do the when the roots are real but unequal. So x1 is equal to minus b plus ds star den, and so this is x1, x2 is equal to minus b minus ds star den, and write x1, x2, and a better way of writing was shown in the earlier one. Then keep a line over here. Then we write 1. We calculate simply x is equal to minus b star den, because in this case the roots are repeated roots. We write repeated roots, simply x, and then stop end. The problem is that whenever you find that d is 0, the program, due to this statement, jumps here and calculates it correctly. When d is positive, the program jumps to this line, it calculates x1, x2, writes x1, x2, then executes all these statements. So we must stop it. So we write stop over here. And when neither of these two conditions are satisfied, the program goes to its next line, that is, it calculates XR, XI and writes this. Again, to avoid this part, we must write stop. So we see that stop is a logical end of a program. So whenever a program encounters a stop statement, it stops right there. In this program, I have used stop in 3 occasions. Instead of writing stop, we could write go to and assign a statement number to this. In a program, there may be more than one stop as per the requirement of the program, but there should be one end statement which signifies the physical end of the program.